At the end of the first half of this lecture, I asked you this question, and hopefully you've come to the conclusion that the answer must be C. Why? Well, this can't be right because it claims the metal contains no charge carriers, but the metal is made of atoms just like everything else, and so it's full of electrons and protons, so it's got lots of charge carriers. Answer B is claiming that the charge carriers in metals are not mobile, but that's not right. Metals are conductors, and so at least some of the charge carriers in metals must be very mobile. And so we're left with C. Because you are standing on the ground or the floor or something like that, and you are a good conductor, any charge you produce on the metal simply flows away to the earth immediately, and that's why you can't charge it. You can charge a metal by rubbing if you insulate it from ground. So for example, when an airplane flies through a cloud, the water droplets rubbing on the metal skin of the plane charge the plane. If you've looked out the window, you might have noticed these pointy things sticking off the rear edges of the wings. Those are so that the charge on the plane collects on the sharp points. We'll see in the course later why charge collects on the sharp points. But the purpose of this is just that having charge all over the skin of the airplane interferes with the operation of various of the plane's electronics. It was once thought that charge might be a fluid that moves inside objects, but we now know that all charge is carried by charged particles. And so because of that, charge only comes in discrete amounts, because we can only transfer integer numbers of particles between objects. As a result, charge always comes in integer multiples of what is called the fundamental charge unit, E, which is just a particular positive amount of charge. The charge on a proton is positive E plus 1e. The charge of an electron is negative E. Inside solids, only electrons can be mobile. The protons are locked up in the nuclei, and the nuclei do not move around appreciably inside a solid. But when charge is transferred from one solid to another, it can be electrons transferred, or it can be chunks of the surface of one or both objects breaking off, so that there are molecular ions, which can be positively or negatively charged, and those are transferred between the objects. In liquid, the charge carriers are dissolved ions, and the liquid will always contain both positive and negative dissolved ions.
Whether or not an object is a conductor or an insulator is determined by how charge moves around in it. And in solids, that mostly means how electrons move around. So in conductors, such as metals, the important thing to realize is that the electrons aren't really in clouds around individual atoms. They're sort of shared among all the atoms. We could call it a sea of electrons. And so the view that you might want of a metal is that each electron is free to just move around anywhere, and the nuclei are sort of hovering in this sea of electrons. Now, in fact, there are all sorts of things wrong with that picture. It's not just the nuclei, because it's only the valence electrons that are allowed to move around freely. But that's good enough. Insulators are totally different, though. In insulators, the electrons are more or less locked within the atoms or molecules that they belong to. And so they really hardly ever move out. It's very difficult to get them to move out, and that's why charge doesn't flow well in the insulator. We started off looking at charging objects by rubbing them, and generally when we're charging insulators, that's how we do it. Conductors are different, and so it's worth understanding a little bit about the differences between insulators and conductors and how they charge. So when we are charging insulators, what's going on is that the insulator is typically made out of molecules. So here's some molecule made out of atoms with bonds connecting them. If you break a bond in the molecule, often it'll break up in such a way that you get two fragments, and often the charge will be unevenly distributed between them, so that one of these fragments is negatively charged and the other is positively charged. You call these molecular ions. Now, if you have two materials, so here's insulator 1 and insulator 2, and I've drawn insulator 1 as being made out of the molecules I was just showing you. Insulator 2, of course, is also made out of molecules, but I'm not bothering to show you them because there's nothing going to happen with them. Now let's say we rub these two insulators together. What can happen when we rub them together is that we cause a bunch of bonds on the surface of this insulator to break. And so we get some of the molecular ions, say the negative ones, left behind on insulator 1, and the positive ones transferred over to insulator 2. But don't think that it's always the positive ones that get transferred. When you're rubbing insulators together, you can get positively charged or negatively charged molecular ions transferred. The transfer can go either way, and in fact there may be a whole lot of different kinds of molecular ions being formed. And this process is basically different for every pair of insulating materials that you rub together. This is very, very complicated, and really it comes down to surface chemistry because you're modifying molecules on the surface because of their interactions with the other surface that it's rubbing against.
In contrast to the very complicated surface chemistry that goes on when we're rubbing insulators together, charging conductors, which is usually by transfer, not rubbing, is relatively simple physics. Only electrons are free to move inside the metals, and they're very free to move, and they're in fact relatively free to leave the metal. And so it's almost always electrons that are transferred into or out of the metal whenever we charge a metal by touching it. So when we touch a negatively charged, say, plastic rod to a metal, what is usually going to happen is that electrons are transferred out of the negatively charged plastic rod and into the metal. And if we touch the metal with a positively charged rod, such as a glass rod that we've rubbed with silk, then what will usually happen is that electrons will be transferred out of the metal and onto the surface of the glass. So all the charging we've seen is either by rubbing, or the very similar pulling apart of things that are stuck together, or by charge transfer. And the key thing to notice is that no charge is actually created in either process. All we're doing is transporting electrons and protons around. And note that we rarely transport just protons. The protons are being transported because they're in the nuclei of atoms that are parts of molecular ions. And so overall, charge is conserved in all of these processes. In those everyday processes, like rubbing things together and transferring charge from a charged object to a neutral one, electrons and protons are never created or destroyed. However, electrons and protons can be created and destroyed in nuclear processes. Is charge still conserved when this happens? Well, here's an example. When an electron meets its antiparticle opposite, the positron, they annihilate to produce gamma rays. But think of the system as the electron and positron, and after the collision as those gamma rays. Then the charge of the system before the annihilation is +1 fundamental charge unit on the positron and -1 charge unit on the electron, and so it adds up to 0. And the gamma rays are uncharged, and so the charge of the system is 0 both before and after the process. Charge has been conserved. Similarly, in neutron decay, the charge is initially 0 because the neutron has no charge. And after the decay, there's a proton with +1 fundamental charge unit, an electron with -1 fundamental charge unit, and an antineutrino which is uncharged. And so once again, the charge is 0 both before and after the process. And these are just some examples. Charge is always conserved in these processes. We have never observed any process which violates conservation of charge. And so experiment tells us that conservation of charge is a universal law, just like the conservation of momentum and the conservation of energy.